Robots that feed on robots, the future of self-sustaining robot ecologies. Advanced robotics pioneer technology enables machines to evolve beyond their physical boundaries by consuming and integrating resources from other robots. This breakthrough, developed by researchers at Columbia University under DARPA funding, marks a significant leap towards self-sustaining ecological systems. Unlike biological organisms, which adapt through integration of materials and components, modern robotic bodies lack the ability to grow, repair, or improve themselves independently. However, this limitation has led to a critical gap in robot autonomy, as closed-loop systems struggle to adapt to their environments. A new era of innovation begins when these robots can learn from one another, mimicking biological processes to enhance functionality. Researchers argue that true autonomy requires not just cognitive expansion, but also physical resilience, a concept that has been realized in biological systems through modular structures and adaptive materials. By imitating nature's approach, building complex structures from simple parts, we may unlock a future where autonomous robots can thrive in diverse environments. This research bridges the gap between artificial intelligence and real-world applications, offering a blueprint for robots that can grow, adapt, and even reproduce autonomously. Revolutionizing robotics. How robot metabolism enables self-repairing machines. Imagine a world where machines can heal themselves without human help, like living organisms that repair their own bodies. This revolutionary concept, called robot metabolism, is reshaping how we think about robotics. Researchers at Columbia University have unveiled a groundbreaking idea: robots that can physically grow, heal, and improve through self-sustaining processes, much like how humans rely on their bodies to recover from injuries. But here's where it gets controversial. Can machines truly mimic the complexity of biological systems without relying on human intervention? The challenge lies in designing robotic bodies that aren't just rigid and dependent on humans for repairs. When a robot breaks apart, it's no longer just a machine. It becomes a system that needs to adapt. Traditional robotics relies on external fixes, but the future may involve robots that can autonomously regenerate parts, learn from failures, and evolve over time. Professor Hod Lipson of Columbia explains that adaptation is a core principle of biology. Just as cells reuse amino acids from other life forms to repair damage, researchers believe robots must learn to repurpose components from their environment, whether through scavenging parts from other robots or reusing materials from their surroundings. This concept is being dubbed machine metabolism, and could redefine how machines interact with their physical world. A key innovation is the truss link, a simple yet powerful building block that mimics the flexibility of organic structures. These magnetic connectors can expand, contract, and snap together at angles, forming dynamic shapes. Imagine a two-dimensional structure that can transform into a three-dimensional robot, much like how living organisms adapt to new environments. The team even demonstrated a tetrahedron robot that grew a walking stick to increase its speed by 66.5%, showcasing the potential for self-improvement. This technology has far-reaching implications. In disaster recovery, robots could repair themselves on the fly, saving lives in unpredictable scenarios. In space exploration, these self-repairing machines might build and adapt without human resupply, enabling long-term missions in remote locations. But the question remains: will robots ever achieve true autonomy, or will they remain tools that require constant oversight? Controversially, some argue that replicating biological processes in machines risks creating systems too complex to control, raising ethical concerns about accountability and safety. Others see it as the next step in AI evolution, where machines not only process data, but also physically sustain themselves. As the research highlights, robot metabolism isn't just about survival. It's about creating a new dimension of autonomy, where AI can build, repair, and evolve alongside humans. If successful, this breakthrough could revolutionize industries from healthcare to space exploration, empowering machines to thrive independently. The study, published in Science Advances, underscores the potential for a future where artificial intelligence and physical systems coexist in a symbiotic relationship. As the author notes, robot metabolism opens the door to a world where machines can build and adapt, not just as tools but as living entities. Self-growing robots, the future of autonomous machines. Imagine a world where robots can grow, heal, and adapt just like living organisms. This groundbreaking concept is no longer science fiction. It's becoming a reality thanks to innovative research at Columbia University. Scientists have developed robots capable of growing, repairing themselves, and evolving by absorbing and reusing materials from their environment or even from other robots. This revolutionary process is known as robot metabolism, and it's set to redefine what autonomy means for machines. Published in the prestigious journal Science Advances, this study introduces a game-changing approach to robotics. Traditional robots are limited by their static, closed system designs, unable to adapt or repair themselves. But here's where it gets controversial. What if robots could not only think for themselves but also physically sustain and improve their own structures? This is the core idea behind robot metabolism, which mimics the way biological life absorbs and integrates resources from its surroundings. True autonomy means robots must not only think for themselves but also physically sustain themselves, explains Philippe Martin-Wider, the lead author and researcher at Columbia Engineering and the University of Washington. Just as living organisms grow, adapt, and repair using materials from their environment, these robots do the same. To demonstrate this concept, researchers created the Truss Link, a robotic magnet stick inspired by the popular Geomag toy. Each truss link is a simple, bar-shaped module with magnetic connectors that allow it to expand, contract, and connect with other modules at various angles. This modular design enables the creation of increasingly complex structures. For instance, individual truss links can self-assemble into two-dimensional shapes, which can then morph into three-dimensional robots. These robots can further enhance themselves by integrating new parts, effectively growing into more capable machines. In one experiment, a tetrahedron-shaped robot added an extra link that functioned like a walking stick, increasing its downhill speed by over 66.5%. This example highlights the potential for robots to adapt and improve their functionality in real time, much like how living organisms evolve to better suit their environments. Robot minds have made significant strides through machine learning in the past decade, but robot bodies remain static and unadaptive, says Hod Lipson, co-author and professor at Columbia University. Biological bodies, on the other hand, are all about adaptation. They grow, heal, and adapt. This ability comes from the modular nature of biology, which can use and reuse building blocks like amino acids. Robots need to learn to do the same, to use and reuse parts from other robots. The researchers envision a future where robots can maintain themselves independently, growing and adapting to new tasks and environments. By mimicking nature's approach of building complex structures from simple components, robot metabolism opens the door to truly autonomous machines capable of physical development and long-term resilience. Robot metabolism provides a digital interface to the physical world, allowing AI to advance not just cognitively but also physically, says Wider. Initially, this technology will be used in specialized applications like disaster recovery or space exploration. Ultimately, it could lead to a world where AI can build physical structures or robots just as easily as it writes or rearranges words in an email today. However, Lipson sounds a note of caution. The idea of self-reproducing robots might bring to mind some scary sci-fi scenarios. But the reality is that as we rely more on robots, from driverless cars to automated manufacturing and even defense and space exploration, we need them to take care of themselves. We can't depend on humans to maintain these machines. Robots must learn to do it themselves. And this is the part most people miss. The potential for self-sustaining robots raises important ethical and practical questions. Should we embrace this technology wholeheartedly? Or are there risks we need to consider? What if these robots evolve in ways we didn't anticipate? The future of robotics is exciting, but it's also a conversation we need to have openly. So what do you think? Are self-growing, self-repairing robots the next big leap in technology, or are we playing with fire? Share your thoughts in the comments. We'd love to hear your perspective.